Okay, I'm doing another example of Mason's formula. Uh, so far, we've done it from input node to output node. In a second, we'll do it between other nodes. But let's do this one from end to end. Let's look at all the loops. Got this guy here, this minus G1 or G1 minus H1 loop. This guy here, G3 minus H2. See what else do we have? See this sort of big loop here? One G2, G3 minus H3. It's a loop. It only touches each node there once. And then this one up here is almost the same. It'll be G4, G3 minus H3. So I'm going to say 4 loops. We'll get into how to find hard to find loops later. You could start at any node, see if you can get back to it without hitting the same node twice. But you'll find that some of them are the same loop. So sometimes you might have to write it down on a notepad. But anyway, there's 4 loops. 2 of them don't touch each other. This guy here and this guy here. Other than that, all 4 loops touch each other. And what about the forward paths? Well, we've got the one straight down the middle, which will touch all 4 loops. And we've got this guy goes over the top through G4. That's two paths, and that guy touches all the loops as well. Yeah, this node touches 3 of the loops, and then he comes back here and he touches both the nodes in that other loop. So both paths touch all loops. So what's the overall delta? It's 1 minus the 4 individual loops, and they all have minuses in them. So when you minus them, they become pluses. So there we are, 1, 2, 3, 4. They're just 4 individual loop gains. And then we had 1 pair of 2 loops that didn't touch, but it's 1 pair. This loop and this loop, that pair gain is the product of all of those gains in those 2 loops. It'll be G1, G3, then the minuses cancel, H1, H2. We added those, and these minus signs canceled, so everything was an add. But this is the 1 pair gain. And what's in the numerator? Both paths touched all loops. So the deltas are 1, so all it is the sum of the 2 individual path gains. G1, G2, G3, and then G4, G3. That's that guy. Now, what if you don't want to go all the way to an output? Let's take this guy and say we're only interested in the transfer function from Y1 to Y2. It is not just 1. Remember, this means everything coming into it gets added. So what's here is not just what's here. It's the sum of that, Y1, plus the sum of minus H3, Y5, minus H1, Y3. So anyway, how do you do that? Well, it's the same 4 loops. It's going to be the same determinant, the big delta on the bottom. That's the same one as it was that we just did. But this path here from Y1 to Y2 doesn't touch this loop out here. It touches the other 3, but not that one. Just that one loop. So what goes up in the top, that minor determinant is 1 minus this guy's loop gain, which is a minus H2 G3. So the minuses cancel, I have plus G3 H2. So that's the transfer function just from Y1 to Y2. Sorry if you're hearing the noise. They're repairing the water main to my house outside. What if you start at a node other than your actual input node? There you use a ratio. Let's see, what if, let's see, what I'm out, let's say I want to, what's the transfer function from Y2 to Y5? I ratio to individual. I always have to start at an input. So this ratio, Y5 over Y2 is Y5 over Y1 over Y2 over Y. And I could find those two guys. In fact, I just did. This top part we did, well, the bottom part we did just on the previous chart. And the top part we did 2 charts. So we already had these two guys, but the big deltas canceled, and I'm just left with the numerators. This is the transfer function from Y2 to Y5. So if you're asked for a transfer function from a node that is not the input node, you must use this ratio method. I guess I got time for this one chart. Remember we saw this before? Here was the overall delta because we had not only individual loops and not only 3 pairs of loops, we had a triplet. So here was the overall determinant for the whole thing. And we did from Y1 to Y5, it was G1, G2 over that delta. Y1 to Y3 doesn't touch this loop. So its gain, E1, that gets you to Y3, minus or times that minor determinant, which is 1 minus this loop gain. If I only went from Y1 to Y2, that path does not touch either of these 2 loops. So the gain by itself is just 1. Still the same overall determinant because I'm still starting from the input. I have to subtract off the 2 individual loop gains, which are H2 and H3, and then add the pairs of non-touching. Remember, this is Y1 to Y2. It only goes to there. It doesn't touch either one of these guys, and these guys don't touch each other. So I add the product of the gains, the pair of loops, H2, H3. So these are three transfer functions, each starting at the input node. Now say I want from node 2 to node 5. I ratio. Here's 5, here's 2. I just ratio the numerators. 1 G2 over this guy. And if I went from Y2 to Y3, Y2 to Y3, I ratio. I had here's the 3. What's that numerator? That numerator. That's how you do from other than input nodes and output nodes. Getting through this, we're almost through Mason's rule.